Tonight, we're going to look at something you can actually see with your naked eye on a clear, dark night. A faint smudge of light in the constellation Andromeda. It looks tiny. It looks like almost nothing. But here's what most people don't realize. That faint smudge is an entire galaxy. And it's not just any galaxy. It's a monster. Andromeda is so enormous that if you could somehow see its full extent in the night sky, it would stretch across a patch of sky 6 times wider than the full moon. It contains roughly 1 trillion stars. And when you truly understand its scale, when you compare its structure by structure against our own Milky Way, something uncomfortable happens. Our galaxy starts to feel small, and that changes everything. Before we go any further, if you find this kind of deep exploration of the cosmos interesting, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Also, before we begin, we're now live on Spotify. The link's in the description if you'd like to listen to us wherever you are. Now, let's begin. Let's start with something you can do tonight if the sky is clear and dark enough. Go outside, find the constellation Andromeda, and look for a faint smudge of light, just barely visible to the naked eye. It doesn't look like much. Most people would walk right past it without a second thought. It looks like a tiny, slightly fuzzy star, maybe a distant cloud of gas, maybe nothing at all. But that faint smudge is the most distant object most humans will ever see without a telescope. And it's not a star. It's not a cloud. It's an entire galaxy. A galaxy containing roughly 1 trillion stars. 1 trillion separate suns, each one potentially hosting its own system of planets and moons. And it's so enormous that if you could somehow see its full extent in the sky, if your eyes were sensitive enough to pick up all of its faint outer light, it would stretch across a patch of sky about 6 times wider than the full moon. That's how big Andromeda appears from Earth. Not a point. Not a tiny smudge. A structure so vast it dwarfs the full moon in apparent size, but most of its light is too faint for your eyes to detect. So you only see the bright central core. The rest is invisible, hidden in plain sight. And here's the thing that makes Andromeda truly remarkable. It's not some exotic distant object billions of light years away. It's our neighbor. It's the nearest major galaxy to the Milky Way. And when you start comparing it to our own galaxy, when you lay the two side by side and measure them structure by structure, something uncomfortable starts to emerge. Andromeda is bigger, not just a little bigger, significantly bigger in almost every way that matters. Its stellar disk is more than twice the diameter of the Milky Way's. It contains roughly 2 to 3 times more stars. Its halo of old stars extends so far into space that it nearly reaches our own galaxy. Andromeda is a giant and we live next door to it. But before we get into those numbers, we need to understand how we figured out what Andromeda actually is. Because for most of human history, nobody knew. Nobody even suspected that what they were seeing was a separate galaxy. They couldn't have, because the concept of galaxies beyond our own didn't exist yet. The earliest known written record of Andromeda comes from the Persian astronomer Abd al-Rahman al-Sufi, who described it in his Book of Fixed Stars around the year 964. He called it a small cloud. That's it, a small cloud. He noted its position in the sky, recorded it carefully alongside hundreds of other stars and objects, and moved on. To him, it was just another feature of the heavens, unremarkable and unexplained. For centuries, that's all it was. A curiosity, a faint blur that defied easy categorization. In 1612, the German astronomer Simon Marius became one of the first people to point a telescope at it. He described the light as resembling the glow of a candle shining through a piece of horn. A soft, diffuse light without clear edges. He couldn't resolve it into individual stars. He couldn't determine its distance. He simply recorded what he saw and noted that it was unlike any star he had observed. Then, in 1764, the French astronomer Charles Messier added it to his famous catalogue of objects that were not comets. Messier was primarily a comet hunter, and he kept finding these annoying fuzzy objects that looked like comets through his telescope, but didn't move across the sky the way comets do. To avoid wasting time on them in the future, he started cataloguing them. Andromeda became the 31st entry in his catalogue, which is why it's known today as M31, or Messier A31. It also carries the designation NGC224 in a later and more comprehensive catalogue of deep sky objects. But here's what's important to understand. When Messier catalogued it, when Marius observed it, when Al-Sufi described it, none of them knew what it was. They assumed it was some kind of nebula, a cloud of gas within our own Milky Way. This was the natural assumption because in the 18th and 19th centuries, most astronomers believed the Milky Way was the entire universe. Everything that existed, every star, every nebula, every cluster was thought to be contained within our galaxy. There was nothing beyond it. The Milky Way was everything. There were hints that this might not be true. As early as 1755, the German philosopher Immanuel Kant proposed that some of the fuzzy nebulae visible in telescopes might actually be what he called island universes. Separate collections of stars so distant that they appeared as faint smudges rather than individual points of light. It was a remarkable idea, especially for the time. Kant had no evidence for it. He was reasoning from analogy and philosophy, not from observation. But the concept was out there, floating in the scientific conversation for over a century, waiting for someone to prove or disprove it. The technology to settle the question didn't exist yet. Telescopes weren't powerful enough. Photography hadn't been applied to astronomy. Spectroscopy, the technique of splitting light into its component wavelengths to learn about an object's composition and motion, was still in its infancy. So the question lingered. Were the spiral nebulae, as they were called, clouds of gas within the Milky Way? Or were they separate galaxies far beyond it? By the late 1800s, the question had become one of the most heated debates in astronomy. In 1888, Isaac Roberts took one of the first long-exposure photographs of Andromeda. The image revealed a spiral structure, arms of light winding outward from a bright central core. This was extraordinary. Whatever Andromeda was, it had structure. It wasn't a formless blob. It had arms, a center, and a shape that suggested rotation and organization. But even this didn't settle the debate because some astronomers argued that spiral structure could exist in a gas cloud within our galaxy. They pointed to other nebulae that had been confirmed as gas clouds and suggested the spirals were simply a different variety of the same thing. The debate came to a head on April 26, 1920, in an event that astronomers now call the Great Debate. It took place at the Smithsonian Museum of Natural History in Washington, D.C. Two prominent astronomers stood before their colleagues and argued opposite sides of the question. On one side was Harlow Shapley. Shapley had recently made groundbreaking measurements of the Milky Way's size, showing it was far larger than previously thought. He estimated the Milky Way was about 300,000 light-years across, which was roughly 3 times larger than earlier estimates. Shapley argued that the Milky Way was so large that it could contain everything, including the spiral nebulae. He believed these nebulae were relatively nearby gas clouds within our galaxy. There was no need to invoke anything beyond the Milky Way. On the other side was Heber Curtis. Curtis argued that the spiral nebulae were separate galaxies, island universes far beyond the Milky Way. He pointed to several pieces of evidence. Novae, which are sudden brightening events in stars, had been observed in Andromeda. If Andromeda was within the Milky Way, these novae would have been extraordinarily bright. But if Andromeda was millions of light years away, the novae would be consistent with known types of stellar explosions at great distance. Curtis also noted that dark dust lanes visible in edge-on spiral nebulae looked similar to the dust lanes known to exist in the Milky Way, suggesting the spirals were similar structures seen from the outside. Neither man could definitively prove his case that night. The debate ended without a clear winner. Both sides had evidence and both sides had weaknesses in their arguments. Shapley's estimate of the Milky Way's size was actually too large, which made it easier for him to argue that everything fit inside it. Curtis's evidence for external galaxies was suggestive, but not conclusive. The question remained open. What changed everything was a telescope, and a woman's earlier discovery that made it all possible. In 1912, Henrietta Leavitt, an astronomer working at Harvard College Observatory, had discovered a remarkable relationship in a type of star called a Cepheid variable. These stars pulsate, brightening and dimming in regular cycles. Leavitt found that the period of a Cepheid's pulsation, the time it takes to go from bright to dim and back again, is directly related to its intrinsic luminosity. A Cepheid that pulsates slowly is genuinely brighter than one that pulsates quickly. This was a breakthrough because it meant that if you could find a Cepheid and measure how long its pulsation cycle takes, you could calculate how bright it actually is. Then, by comparing that true brightness to how bright it appears from Earth, you could calculate how far away it is. The dimmer it appears relative to its true brightness, the farther away it must be. This gave astronomers a cosmic ruler, a way to measure distances to objects far beyond what parallax measurements could reach. In 1923, an American astronomer named Edwin Hubble was using the 100-inch Hooker telescope at Mount Wilson Observatory in California. At the time, it was the most powerful telescope in the world. Hubble trained it on Andromeda and began taking long exposure photographs, night after night. He was looking for novae, the same type of stellar brightening events that Curtis had pointed to during the Great Debate, and he found them. But then he found something far more important. In one of his photographic plates, Hubble identified a star in Andromeda that wasn't a nova at all. It was a Cepheid variable. He marked it with the letters VAR on the photographic plate and added an exclamation point. He knew immediately what this meant. Using Leavitt's period luminosity relationship, Hubble measured the Cepheid's pulsation period and calculated its true brightness. Then, he compared that to how bright it appeared in his photographs. The result was staggering. The Cepheid was far too distant to be inside the Milky Way. Andromeda wasn't a nearby gas cloud within our galaxy. It was a separate galaxy, an island universe in its own right, roughly 900,000 light-years away by Hubble's initial calculation. That number was later revised upward as astronomers refined their distance measurements. Today, we know the true distance is about 2.5 million light years. But even Hubble's initial lower estimate was enough to shatter the old view of the cosmos. Andromeda was beyond the Milky Way, far beyond it. And if Andromeda was a separate galaxy, then the other spiral nebulae probably were too. The universe had just gotten incomprehensibly larger. Hubble formally presented his findings on January 1st, 1925, at a meeting of the American Astronomical Society. The reaction was immediate. Shapley, upon learning of Hubble's results, reportedly said that the letter containing the evidence had destroyed his universe. He meant it metaphorically. The Milky Way was no longer everything. It was just one galaxy among many. The cosmos had expanded from a single galaxy to a universe filled with galaxies, each one containing billions of stars, each one separated from the others by millions of light years of empty space. This was one of the most profound shifts in human understanding of the cosmos. For centuries, the Milky Way had been the universe. Now it was just a neighborhood. And Andromeda, that faint smudge that ancient astronomers had dismissed as a small cloud, turned out to be a galaxy larger than our own. So what exactly is Andromeda in physical terms? Let's lay out the facts, because the numbers themselves tell a story that words alone cannot fully capture. Andromeda is a barred spiral galaxy. Like the Milky Way, it has a flat rotating disk of stars, gas and dust, with spiral arms winding outward from a central region. Recent infrared observations from the Spitzer Space Telescope confirm that Andromeda has a bar-shaped structure at its center, a dense, elongated concentration of stars that extends outward from the core before the spiral arms begin. This makes it a barred spiral, similar in basic type to the Milky Way, though larger and more massive in nearly every measurable dimension. The visible stellar disk of Andromeda stretches about 220,000 light years from one side to the other. The Milky Way's disk, by comparison, is roughly 100,000 light years across, though some recent estimates push it close to 180,000 light years when you include the faint outer extensions. Even using the most generous estimates for the Milky Way, Andromeda's disk is still significantly wider. In the most straightforward comparison, Andromeda's stellar disk is more than twice the diameter of the Milky Way's. Andromeda contains roughly 1 trillion stars. That's 1 trillion individual suns, each one a furnace of nuclear fusion, each one potentially hosting planets. The Milky Way contains somewhere between 100 billion and 400 billion stars, with most estimates centering around 200 to 300 billion. This means Andromeda likely contains 2 to 3 times more stars than our galaxy. In raw stellar population, Andromeda is the larger galaxy by a considerable margin. The mass comparison is more complex because most of a galaxy's mass isn't in its stars. It's in dark matter, the invisible substance that we can't see directly but whose gravitational effects we can measure. For years, astronomers estimated Andromeda's total mass, including dark matter, at about 1.5 trillion times the mass of our Sun, making it significantly more massive than the Milky Way. More recent studies using data from the Gaia spacecraft have complicated this picture somewhat, suggesting the Milky Way might be more massive than previously thought, and Andromeda might be somewhat less massive. Some recent estimates put both galaxies in a similar mass range, roughly 1 to 1.5 trillion solar masses each. But even in the most conservative estimates, Andromeda is at least comparable to the Milky Way in total mass, and almost certainly exceeds it in visible matter, star count, and disk size. Andromeda is the dominant galaxy of the local group. The local group is the collection of roughly 50 galaxies in our immediate cosmic neighborhood, spanning about 10 million light years. The Milky Way and Andromeda are the two giants of this group, with every other member being significantly smaller. The Triangulum Galaxy, also called M33, is the third largest, but it contains only about 40 billion stars and spans roughly 60,000 light years. It's less than a third the diameter of Andromeda and has only a fraction of its stellar population. The rest of the local group consists of dwarf galaxies, small collections of a few billion or even a few million stars. Some of these dwarfs orbit the Milky Way, like the large and small Magellanic Clouds. Others orbit Andromeda like M32 and M110. But the two dominant members, the gravitational anchors of the entire group, are the Milky Way and Andromeda. And of the two, Andromeda is the larger. This is an important point to sit with for a moment. In our cosmic neighborhood, the Milky Way is not the biggest galaxy. It's the second biggest. Andromeda holds that title. And it doesn't hold it narrowly. It holds it with a disk more than twice the diameter of ours, and a star count that may be 3 times higher. If the local group were a neighborhood, the Milky Way would be a large, impressive house, but Andromeda would be the mansion on the hill, visible from every other house, dominating the skyline. Now, there's a subtlety here that's worth addressing. When astronomers say the Milky Way is one of the largest galaxies in the universe, they're comparing it to the overall population of galaxies. About 95% of all galaxies are smaller than the Milky Way. Most galaxies are dwarf galaxies, tiny and faint. So in the grand cosmic census, the Milky Way is genuinely large. It's in the top 5%. That's impressive and that's real, but within our own local neighborhood, within the local group, the Milky Way isn't the top. Andromeda is. And the gap between them is not trivial. Here's another way to think about it. If you were an astronomer living in a galaxy far away, looking at the local group through a powerful telescope, the first thing you'd notice is Andromeda. It would be the brightest, most prominent member. The Milky Way would be the second thing you'd notice. You might initially mistake the local group for Andromeda's group, with the Milky Way as one of its larger satellites. That's how much Andromeda dominates our corner of the universe. What makes this even more striking is that we can see Andromeda with the naked eye. Think about what that means. An entire galaxy containing 1 trillion stars spread across 220,000 light years of space is close enough and bright enough that a human being standing on Earth can detect its light without any technology at all. The photons that enter your eye when you look at Andromeda tonight left that galaxy about 2.5 million years ago, when early human ancestors were just beginning to use simple stone tools on the plains of Africa. Those photons have been traveling through the void of intergalactic space for 2.5 million years at 300,000 kilometers per second. And tonight, they complete their journey by landing on your retina. You're seeing Andromeda as it was 2.5 million years ago. Not as it is right now, but as it was when the genus Homo was just emerging on Earth. The Andromeda you see tonight is ancient light, a message from the deep past, traveling across the deep emptiness between galaxies to reach you. And yet, despite being 2.5 million light years away, a distance so vast that the light takes 2.5 million years to cross it, Andromeda is considered our neighbor. In cosmic terms, it's right next door. The observable universe is 93 billion light-years across. The nearest large galaxy cluster, the Virgo cluster, is about 54 million light-years away. In this context, 2.5 million light-years is nothing. It's like living in New York and having a neighbor in New Jersey. Yes, there's a gap between you, but compared to the distance to Tokyo or Sydney, you're practically on top of each other. This is one of the first things that makes Andromeda so remarkable. It is close enough to study in extraordinary detail. We can resolve individual stars in Andromeda. We can identify star clusters, dust lanes, and regions of active star formation. We can map its spiral structure, measure the rotation of its disk, and study the orbits of its satellite galaxies. We can do with Andromeda something we cannot do with our own galaxy. We can see it from the outside. That's a crucial point. We live inside the Milky Way. We're embedded in its disk, surrounded by its dust and stars on all sides. Trying to understand the Milky Way's structure from our position inside it is like trying to understand the shape of a forest while standing among the trees. You can see the trees around you, but you can't see the forest's outline. You can't see its overall shape, its boundaries, its full extent. Dust blocks your view in many directions. Distant stars blur together. The center of the galaxy is hidden behind thick clouds of interstellar dust that visible light cannot penetrate. We've learned a tremendous amount about the Milky Way using infrared and radio observations that can see through dust, but we've never had and never will have an outside view of our own galaxy. Andromeda gives us the next best thing. It's a large spiral galaxy similar to the Milky Way in basic type, close enough to study in detail, and visible from the outside. When astronomers study Andromeda, they're partly studying our own galaxy by proxy. They're seeing what a major spiral galaxy looks like from an external vantage point. Andromeda is a mirror, a way of understanding ourselves by studying something similar from the outside. But it's not a perfect mirror, because as we're about to discover, Andromeda isn't just similar to the Milky Way, it's significantly larger. And that difference in scale reveals something important about what galaxies really are and how limited our perspective from inside the Milky Way truly is. When you start peeling back the layers of Andromeda, when you look beyond the visible disk to the halo, the dark matter envelope, the satellite system, and the extended structures that reach far beyond what any casual image shows, the true scale of this galaxy becomes almost overwhelming. And the Milky Way, our home, starts to feel like something smaller than we ever imagined. When most people think about a galaxy's size, they think about one number, a diameter. How wide is it from one side to the other? And for casual conversation, that's fine. But the truth is that a galaxy's size is not one number, it's layers. A galaxy doesn't simply stop at some clean defined edge the way a planet does. There's no surface, no boundary, no wall where the galaxy ends and empty space begins. Instead, a galaxy fades. It thins out. Its stars become sparser, its gas more diffuse, its influence more subtle, but it keeps going. Far beyond what any photograph shows, far beyond what most people imagine when they picture a galaxy in their minds. And understanding these layers, understanding the difference between the bright visible core, the stellar disk, the extended halo, and the dark matter envelope is essential to grasping the true scale of Andromeda. Because when you look at Andromeda through a telescope, when you see those beautiful photographs of its spiral arms glowing against the darkness, you're only seeing a fraction of what's actually there. The real Andromeda is vastly larger than what any image shows, and when you compare each layer of Andromeda to the equivalent layer of the Milky Way, the gap between the two galaxies becomes even more striking than a simple diameter comparison would suggest. Let's start with the part you can see, the stellar disk. This is what most people think of when they picture a galaxy. It's the flat, pancake-shaped structure where the spiral arms live. The disk contains the majority of a galaxy's young stars, its gas, its dust, and its regions of active star formation. When you look at a photograph of Andromeda, the bright, elongated oval of light you see is the disk viewed at a slight angle. Andromeda's disk is tilted about 77 degrees from our line of sight, which means we're seeing it nearly edge on, but not quite. This angle gives us a beautiful view of its overall shape, while still allowing us to see some of the spiral structure within it. Andromeda's stellar disk stretches about 220,000 light years from one edge to the other. Let me put that in context. Light, which travels at about 300,000 kilometers per second, the fastest speed anything in the universe can achieve, would need 220,000 years to cross Andromeda's disk. If a beam of light left one side of Andromeda when the first modern humans were developing language and symbolic thought, that light would still have a long journey ahead before reaching the other side. That's the scale we're talking about. The Milky Way's disk, by comparison, is roughly 100,000 to 180,000 light years across, depending on which study you reference and how you define the outer boundary. The traditional estimate has been about 100,000 light years. More recent surveys have pushed that number higher by detecting faint populations of stars in the galaxy's outer regions that earlier surveys missed. Even using the most generous estimates for the Milky Way, Andromeda's disk is still notably wider. Using the traditional estimates, Andromeda's disk is more than twice the Milky Way's diameter. And it's not just wider. Andromeda's disk contains more stuff, more stars, more gas, more dust, more of the raw material from which new stars form. Andromeda contains roughly 1 trillion stars compared to the Milky Way's estimated 200 to 400 billion. That difference matters because it means Andromeda's disk is not just wider, but denser in stellar population. There are more stars packed into each region of the disk, particularly in the inner portions near the galaxy's center. Now, if you were to look at Andromeda's disk in detail, you'd see several distinct features. There's a prominent dust ring at a radius of about 32,000 light years from the center. This ring is a region where gas and dust are concentrated, and it's where much of the galaxy's current star formation is happening. Inside this ring, the disk is relatively clear of dust. Outside it, there are additional rings and spiral arm segments extending outward. This ring structure is thought to be the result of a past gravitational interaction, possibly a close encounter with M32, one of Andromeda's satellite galaxies, which may have plunged through the disk millions of years ago, sending ripples through the gas and dust like a stone dropped into a pond. The Milky Way has its own spiral arms and star-forming regions, of course, but here's the disadvantage we face when comparing the two. We can see Andromeda's disk from the outside. We can map its full extent, trace its spiral arms, measure its dust lanes, and catalogue its star-forming regions with relative ease. We can't do that with our own galaxy because we're inside it. Trying to map the Milky Way's disk from our position within it is like trying to draw a map of an entire city while standing in one room of one building. You can see some things clearly, but the full picture is hidden. Dust blocks our view toward the galactic center and along the plane of the disk. Stars in the far side of the galaxy are obscured. We've made tremendous progress using infrared and radio telescopes that can see through dust, and spacecraft like Gaia have mapped the positions of nearly 2 billion stars in our galaxy. But we still don't have the kind of clear, complete outside view that we have of Andromeda. This is one reason why Andromeda is so scientifically valuable. It gives us a template. It shows us what a major spiral galaxy looks like from the outside, which helps us understand our own galaxy's structure by comparison. But the stellar disk, impressive as it is just the beginning. Because galaxies don't end at the edge of their visible disks. Beyond the disk lies something called the stellar halo. And this is where Andromeda's true enormity starts to reveal itself. The stellar halo is a roughly spherical cloud of old stars that surrounds the disk. These aren't the young, bright stars that populate the spiral arms. These are ancient stars, many of them more than 10 billion years old, formed in the earliest epochs of the galaxy's history, or stripped from smaller galaxies that Andromeda consumed over billions of years. The halo stars are spread thinly through an enormous volume of space, far too faint and sparse to show up in most photographs. But they're there, and they extend to astonishing distances. The most comprehensive study of Andromeda's stellar halo was conducted using a program called the Pan-Andromeda Archaeological Survey, a massive observational campaign that mapped individual stars across the entire outskirts of the galaxy and its surrounding environment. What this survey revealed was remarkable. Andromeda's stellar halo extends to at least 500,000 light-years from the galaxy's center. Some detections of halo stars push even farther, possibly reaching 600,000 light-years or more. Let that number register for a moment. 500,000 light-years. The visible disk of Andromeda, the bright part you see in photographs, is about 220,000 light-years across, meaning it extends roughly 110,000 light-years from the center. The stellar halo extends more than 4 times farther. The galaxy you see in images is less than a quarter of the galaxy's full stellar extent. The Milky Way also has a stellar halo. Estimates of its extent vary, but most studies place it at roughly 300,000 to 500,000 light-years in diameter, meaning it extends roughly 150,000 to 250,000 light-years from the center. Andromeda's halo, at 500,000 or more light-years in radius, is significantly larger. This is important because the halo contains a historical record of the galaxy's past. The streams and structures within the halo, tidal streams of stars pulled from devoured dwarf galaxies, shells of debris from ancient mergers, clumps of stars that trace the orbits of long-dead satellite galaxies. All of these tell the story of how Andromeda grew over cosmic time. And what they tell us is that Andromeda has consumed a lot of galaxies. Its halo is rich with substructure, filled with the remnants of dozens of smaller galaxies that fell into Andromeda's gravitational embrace and were torn apart over billions of years. The Milky Way's halo shows similar features, streams and structures from consumed dwarf galaxies. But Andromeda's halo appears to be more extensive and more richly structured, consistent with a larger galaxy that has consumed more material over its lifetime. The most dramatic piece of evidence for Andromeda's violent past is something called the Giant Stellar Stream. This is an enormous river of stars flowing through Andromeda's halo, stretching roughly 200,000 light-years in length. It was first identified in 2001 using wide-field surveys that map the distribution of individual red giant stars across Andromeda's outskirts. What the astronomers found was unmistakable. A coherent arc of stars, all moving in roughly the same direction at roughly the same speed, tracing a long, looping path through the halo. This stream is the remains of a dwarf galaxy that fell into Andromeda and was torn apart by tidal forces. As the smaller galaxy orbited Andromeda, the gravity of the larger galaxy stretched it, pulling stars off its leading and trailing edges, smearing it out into a long ribbon. The original galaxy is gone, destroyed, but its stars remain, tracing the orbit of a galaxy that no longer exists, a ghost orbit drawn in starlight. The giant stellar stream isn't the only such feature. The Pan-Andromeda Archaeological Survey and other deep imaging campaigns have revealed that Andromeda's halo is filled with substructure. There are shells, concentric arcs of stars that form when a smaller galaxy falls almost directly into the center of a larger one, and its stars splash outward like ripples from a stone dropped into water. There are fans, broad wedge-shaped concentrations of stars that indicate a different kind of orbital interaction. There are clumps and overdensities scattered throughout the halo, each one the fossil remains of a separate accretion event, a separate galaxy consumed. In 2018, a team of astronomers published a detailed analysis suggesting that roughly 2 billion years ago, Andromeda underwent a particularly significant merger. A galaxy roughly comparable in size to M33, the Triangulum galaxy appears to have collided with Andromeda and been completely absorbed. This was not a minor event, as this was the consumption of a substantial galaxy, one containing tens of billions of stars. The debris from this merger is thought to account for a large fraction of the substructure visible in Andromeda's halo today. Many of the streams and shells we observe may trace back to this single event. The remnants of one galaxy scattered across hundreds of thousands of light years by the gravitational forces of its destroyer. This discovery has profound implications for understanding the difference between Andromeda and the Milky Way. The Milky Way has also consumed smaller galaxies. The Sagittarius dwarf elliptical galaxy is currently being pulled apart by the Milky Way's gravity, and the Gaia spacecraft has identified streams and debris from other ancient mergers in the Milky Way's halo. But the Milky Way appears to have had a quieter merger history than Andromeda. The largest galaxy the Milky Way consumed, an ancient system sometimes called the Gaia Sausage, or Gaia Enceladus, was significantly smaller than the galaxy Andromeda consumed 2 billion years ago. Andromeda's merger history has been more violent, more active, involving larger prey. And this more active history is written into its halo, recorded in streams and shells and clumps of stars that tell the story of galaxy after galaxy falling in and being destroyed. This is what makes the stellar halo so scientifically valuable. It's not just a cloud of old stars. It's an archive. Every stream is a sentence. Every shell is a paragraph. Every clump is a chapter in the story of how this galaxy grew to its current size. And Andromeda's archive is richer and more detailed than the Milky Way's, consistent with a galaxy that has consumed more material, experienced more mergers, and grown to a larger final size. The halo isn't just evidence that Andromeda is big. It's the record of how Andromeda became big, one consumed galaxy at a time, over billions of years. Now, let's go even further out. Beyond the stellar halo lies something even larger and more diffuse. The circumgalactic medium, a vast envelope of hot, diffuse gas that surrounds the galaxy. In 2015, a team of astronomers using the Hubble Space Telescope's Cosmic Origins spectrograph made a remarkable measurement. They used distant quasars, incredibly bright objects powered by supermassive black holes in faraway galaxies, as background light sources. By observing how Andromeda's gas absorbed specific wavelengths of light from those quasars, the team could map the extent of Andromeda's gaseous halo. What they found was extraordinary. Andromeda's gaseous halo extends to at least 1.3 million light-years from the galaxy's center. That's a diameter of roughly 2.6 million light-years. To put this in perspective, the distance from the Milky Way to Andromeda is about 2.5 million light-years. Andromeda's gaseous halo is so enormous that it extends more than halfway to our own galaxy. In fact, it's quite possible that Andromeda's gaseous halo and the Milky Way's gaseous halo are already touching, already overlapping in the vast space between the two galaxies. The two galaxies may already be in contact through their gas, even though their stellar disks are still separated by millions of light years. If that's the case, then in a very real physical sense, the merger of Andromeda and the Milky Way has already begun, not as a dramatic collision of stars, but as a quiet mingling of gas in the intergalactic void. The Milky Way has its own gaseous halo, but measurements of its extent are more difficult because we're inside it. Estimates suggest it extends to several 100,000 light-years, possibly up to 1 million light-years or more. But even the most generous estimates for the Milky Way's gaseous halo are smaller than what has been measured for Andromeda. Once again, Andromeda is larger. And then there's the dark matter halo, the largest and most massive component of all. Dark matter is the invisible substance that makes up about 85% of all matter in the universe. We can't see it directly. It doesn't emit light, absorb light, or interact with light in any way, but we know it's there because of its gravitational effects. Galaxies rotate faster than they should, based on their visible matter alone. Galaxy clusters are held together by more gravity than their visible matter can account for. The large-scale structure of the universe, the cosmic web of filaments and voids, only makes sense if dark matter exists. Every galaxy sits inside a halo of dark matter that extends far beyond its visible stars and gas. The dark matter halo is the scaffolding, the invisible framework that holds the galaxy together. Without it, the galaxy would fly apart. The stars in the outer regions of the disk orbit so fast that the gravity of the visible matter alone couldn't hold them. Dark matter provides the extra gravitational pull that keeps everything bound. Andromeda's dark matter halo is estimated to extend to roughly 1.5 to 2 million light-years from the galaxy's center. Some models push it even further. The total mass of Andromeda, including its dark matter halo, is estimated at roughly 1 to 1.5 trillion times the mass of our Sun, though this number has been revised multiple times as new data becomes available. The Milky Way's dark matter halo extends to roughly 500,000 to 1 million light-years and contains a similar total mass, roughly 1 to 1.5 trillion solar masses as well. This is one area where the comparison between the two galaxies has become more nuanced in recent years. Earlier estimates suggested Andromeda was significantly more massive than the Milky Way in total mass. More recent studies, particularly those using data from the Gaia spacecraft, which has measured the motions of stars in the Milky Way with unprecedented precision, have suggested that the Milky Way might be somewhat more massive than previously thought, and some studies have revised Andromeda's total mass downward. The current best estimates place the two galaxies in a similar mass range, with Andromeda possibly slightly more massive, or the two being roughly comparable. But even if their total masses, including dark matter, are similar, Andromeda still has a larger visible component, more stars, a wider disk, a more extended stellar halo. The visible galaxy, the part made of ordinary matter that we can actually see and study, is larger in Andromeda by a significant margin. Now, let's talk about Andromeda's satellite galaxies, because this is another dimension of scale that most people don't consider when they think about how big a galaxy is. A galaxy isn't just a collection of stars. It's a gravitational system that includes smaller galaxies orbiting around it, bound to it by gravity, slowly being shaped and sometimes consumed by its influence. Andromeda has a rich system of satellite galaxies. The two most prominent are M32 and M110, also designated NGC 205. M32 is a compact elliptical galaxy that appears to be very close to Andromeda's disk, possibly even embedded in it to some degree. It's small but dense, containing roughly 3 billion stars packed into a region only about 6,500 light-years across. M32 is thought to have once been a much larger galaxy, perhaps comparable to the Triangulum galaxy M33, that lost most of its outer stars through gravitational interactions with Andromeda over billions of years. Andromeda essentially stripped M32 of its outer layers, leaving behind only the dense core. This is galactic cannibalism in action, the larger galaxy consuming the smaller one piece by piece. M110 is different. It's a dwarf elliptical galaxy, larger than M32 in extent but much more diffuse. It contains roughly several billion stars, spread across a wider area, about 15,000 light-years across. M110 has its own interesting features, including rare signs of recent star formation in what is normally a type of galaxy that has long since stopped making new stars. Beyond these two prominent satellites, Andromeda has dozens of smaller dwarf galaxies orbiting it. As of the most recent surveys, astronomers have identified roughly 30 to 40 satellite galaxies around Andromeda, designated by names like Andromeda 1, Andromeda 2, Andromeda 3, and so on. Many of these were discovered through systematic surveys that carefully searched the outskirts of Andromeda for faint overdensities of stars. Subtle concentrations that indicate the presence of a tiny galaxy too faint to see in ordinary images. Some of these dwarf satellites contain only a few million stars. Others contain a few hundred million, but each one is a galaxy in its own right, bound to Andromeda by gravity, orbiting it on timescales of billions of years. There are also galaxies in the local group that may be satellites of Andromeda but are farther out. NGC 147 and NGC 185 are two dwarf galaxies that are gravitationally associated with Andromeda, and are sometimes considered part of its satellite system, even though they're at a greater distance from it. The Milky Way has its own collection of satellite galaxies. In fact, the Milky Way currently has more known satellites than Andromeda, roughly 50 to 60 compared to Andromeda's 30 to 40. But this difference is almost certainly an observational bias rather than a real physical difference. The Milky Way's satellites are closer to us, which makes them easier to detect. The faintest, smallest dwarf galaxies around the Milky Way have been discovered precisely because they're nearby enough for us to resolve their individual stars. Similar galaxies orbiting Andromeda would be much harder to detect at 2.5 million light-years away. Many of Andromeda's faintest satellites are likely still undiscovered, hiding below the detection limits of current surveys. What's more interesting than the raw count is the distribution and organization of these satellites. One remarkable discovery is that many of Andromeda's satellite galaxies appear to be arranged in a thin plane, a vast rotating disk of satellites orbiting the galaxy in a coordinated fashion. This plane of satellites extends roughly 1.3 million light-years across and is oriented roughly perpendicular to Andromeda's disk. The Milky Way has a somewhat similar feature, with many of its satellite galaxies also appearing to lie in a plane. The existence of these satellite planes is actually a challenge for some models of galaxy formation, because standard dark matter simulations don't naturally produce such organized satellite distributions. They predict a more random, spherical arrangement. The fact that both the Milky Way and Andromeda show planar satellite distributions suggests that there may be physical processes at work that our models don't yet fully capture. So when we talk about the size of Andromeda, we need to think about all of these layers together. Not just the bright disk that shows up in photographs, but the full structure. The disk spans about 220,000 light-years. The stellar halo extends to at least 500,000 light-years. The gaseous halo reaches roughly 1.3 million light-years. The dark matter halo may stretch to nearly 2 million light-years. And the satellite system, the constellation of smaller galaxies bound to Andromeda by gravity, extends even farther, with some satellites orbiting at distances of 1 million light-years or more from the center. When you account for all of this, the true Andromeda is not a 220,000 light-year disk. It's a gravitational system that dominates a region of space roughly 3 to 4 million light-years across, if you include the full dark matter halo and the outermost satellites. That's an enormous volume of space, and almost all of it is invisible. The bright disk that you see in photographs, the part that most people think of as the galaxy, represents only the dense, luminous core of a structure that extends far, far beyond what any image reveals. This is true of the Milky Way as well. Our galaxy isn't just a 100,000 light-year disk either. It has its own halo, its own gaseous envelope, its own dark matter framework, its own satellite system. But at nearly every layer, Andromeda's structure is larger, more extended, or more richly populated. The disk is wider. The halo reaches farther. The gaseous envelope extends to greater distances. The satellite population, once accounting for observational biases, is likely comparable or larger. The only area where the Milky Way may hold an advantage is in total mass, including dark matter. And even that is currently uncertain, with recent studies placing the two galaxies in a similar range. When it comes to visible matter, to stars and gas and dust, the stuff that makes up the galaxy you can actually see, Andromeda is the clear winner. Let me offer one more comparison that drives this home. The supermassive black hole at the center of the Milky Way, Sagittarius Ii star, has a mass of about 4 million times the mass of our Sun. It's a substantial object by any standard. 4 million solar masses compressed into a region smaller than the orbit of Mercury. But the supermassive black hole at the center of Andromeda has a mass of roughly 100 to 230 million times the mass of our Sun. Different studies have produced different estimates, but even the most conservative place Andromeda's central black hole at roughly 25 to 50 times more massive than the Milky Way's. The most commonly cited estimate is around 100 million solar masses, which is about 25 times more massive than Sagittarius IY star. Supermassive black holes are thought to grow alongside their host galaxies, accumulating mass as the galaxy grows through mergers and gas accretion. A larger central black hole generally indicates a galaxy with a more extensive history of growth and accretion. Andromeda's much larger central black hole is consistent with it being a galaxy that has consumed more material over its lifetime, growing larger than the Milky Way through a more active history of mergers and gas infall. So, where does all of this leave us? When you tally up every measurable dimension of these two galaxies, the picture is consistent. Andromeda's disk is wider, its star count is higher, its stellar halo extends farther, its gaseous envelope reaches deeper into intergalactic space, its central black hole is more massive. The only dimension where the Milky Way may compete is total mass, including dark matter, and even that is uncertain. The Milky Way is a large, impressive galaxy. It's larger than 95% of all galaxies in the observable universe. It contains hundreds of billions of stars, has an active program of star formation, and hosts a rich system of satellite galaxies. By any reasonable standard, the Milky Way is a cosmic giant. But next to Andromeda, it's the smaller sibling. Not dramatically smaller, not insignificantly smaller, but measurably, consistently smaller across virtually every structural dimension. And here's the part that should really make you pause. We can only see a tiny fraction of Andromeda's true extent. The bright disk, the part visible in photographs and to the naked eye, is the innermost and densest part of a much larger structure that extends for millions of light years into space. If you could somehow illuminate all of Andromeda's dark matter, if you could make its full halo glow, it would dominate the night sky. It would stretch across a vast swath of the heavens, dwarfing every other object visible. The faint smudge you see in the constellation Andromeda is the bright heart of something almost unimaginably vast. A structure so large that its outermost reaches may already be mingling with our own galaxy's outermost reaches. Two great invisible envelopes of gas and dark matter touching across the intergalactic void. A quiet handshake between neighbors that foreshadows a much more dramatic encounter still billions of years in the future. This layered reality, this hidden enormity beyond the visible surface, isn't unique to Andromeda. It applies to all galaxies, including the Milky Way. Every galaxy is far larger than it appears. Every galaxy is an iceberg, with the visible part representing only a small fraction of the total structure. But Andromeda, being both nearby and larger than the Milky Way, makes this truth viscerally real in a way that abstract numbers alone cannot. It shows us that galaxies are not just the bright disks in photographs. They are vast, multi-layered gravitational systems that extend far into the darkness, influencing space for millions of light years in every direction. And the nearest one to us, the largest one in our cosmic neighborhood, is big enough to make even our mighty Milky Way feel like the smaller galaxy in the room. 2.5 million light years. That's the distance from the Milky Way to Andromeda. You've heard that number already in this story, and you'll hear it again. But I don't want it to just be a number. I want you to actually understand what it means. Because when you truly grasp what 2.5 million light years represents as a physical distance, it does something strange to your sense of scale. It makes Andromeda feel both impossibly far away and remarkably close at the same time. And that paradox, that tension between distance and proximity, is one of the most fascinating things about our nearest major galactic neighbor. Let's build up to it. Let's start with distances we can almost relate to and watch them grow until the numbers stop making intuitive sense. Because they will stop making sense. At some point, the distances we're talking about will exceed anything your brain is wired to comprehend. That's not a failure of imagination, it's a limitation of being human. We evolved to understand the distance to the next river, the next hillside, the next village, not the distance to the next galaxy. Start with the Earth and the Moon. The Moon is about 384,000 kilometers away. That's close enough that humans have actually traveled there. Apollo astronauts made the journey in about 3 days, traveling at roughly 11 kilometers per second. The Moon is our closest celestial neighbor, and reaching it required some of the most powerful rockets ever built, some of the most precise engineering ever attempted, and 3 days of travel through empty space. That's our baseline. 3 days to reach the closest thing to Earth in all of space. The Sun is about 150 million kilometers from Earth. That's roughly 400 times the distance to the Moon. Light covers that distance in about 8 minutes and 20 seconds. The fastest spacecraft humans have ever built, the Parker Solar Probe, reaches speeds of up to 192 kilometers per second when it's close to the Sun, and even at that speed, traveling from Earth to the Sun would take months. The Sun is close. It's the star we orbit. It's right here. And yet, it's already far enough away that reaching it is a major undertaking even for our fastest machines. Now, the nearest star beyond the Sun, Proxima Centauri, is about 4.24 light years away. That's roughly 40 trillion kilometers. Let me try to make that real. If you could somehow board a spacecraft, traveling at the speed of the Parker Solar Probe, 192 kilometers per second, you would reach Proxima Centauri in about 6,800 years. That's longer than all of recorded human history. Writing was invented about 5,000 years ago. You could have launched your spacecraft when the first cuneiform tablets were being pressed in Mesopotamia, traveled continuously at the fastest speed any human machine has ever achieved, and you would still not have arrived. You'd still have roughly 2,000 years of travel ahead of you. Proxima Centauri is the closest star, and it's already functionally unreachable with anything we can currently build. So 4.24 light years is an enormous distance. Keep that number in your mind because we're about to multiply it dramatically. The Milky Way is roughly 100,000 light years across. That's about 24,000 times the distance to Proxima Centauri. Even traveling at the speed of light, crossing our own galaxy would take 100,000 years. The last time humans were at a comparable point in history, 100,000 years ago, we were still living as small bands of hunter-gatherers in Africa, sharing the planet with Neanderthals, barely beginning to develop the complex behaviors that would eventually lead to art, language, and civilization. The Milky Way is so large that crossing it at the fastest speed the universe allows would take a span of time longer than the entire history of behavioral modernity in our species. Now, let's take another step. The distance to Andromeda is about 2.5 million light years. That's roughly 25 times the width of the entire Milky Way. Imagine laying 25 Milky Way galaxies end to end in a straight line, each one 100,000 light years across. The distance to Andromeda would stretch across all of them with room to spare. 25 complete galaxies, each containing hundreds of billions of stars, lined up in a row. That's the gap between us and our nearest major neighbor. In kilometers, 2.5 million light years is approximately 23.65 quintillion kilometers. That's 23 followed by 18 zeros. Writing that number out in full would take a line of digits stretching across the page, and every single one of those kilometers is a real physical kilometer. The same distance you might drive in a few minutes on a highway. There are 23.65 quadrillion of them between us and Andromeda. If you could somehow drive a car at highway speed toward Andromeda, traveling at 100 kilometers per hour without stopping, it would take about 27 trillion years to get there. The universe itself is only 13.8 billion years old. You would need roughly 2,000 times the current age of the universe to drive to Andromeda. The universe would be long dead, all its stars burned out, all its energy dissipated, and you'd still be driving, still crossing the void, still unimaginably far from your destination. Let's try another comparison. Voyager 1, launched in 1977, is the most distant human-made object. As of 2025, it's about 24 light hours from Earth, roughly 163 astronomical units. It's been traveling for nearly 50 years at approximately 17 kilometers per second. At that speed, Voyager 1 would need roughly 44 billion years to reach Andromeda. Again, that's more than 3 times the current age of the universe, the fastest thing we've ever launched, traveling continuously for 3 times longer than the cosmos has existed, still wouldn't make it to the nearest major galaxy. These comparisons aren't meant to overwhelm you. They're meant to show you something specific. The distance to Andromeda is not a large number. It's a number so large that it breaks our normal frameworks for understanding distance. It's a number that makes even cosmic distances that are already far beyond human experience, seem small by comparison. The distance to the nearest star is already unreachable. The distance to Andromeda is 600,000 times farther than that. And yet, astronomers call Andromeda nearby. This isn't a joke. It's not an exaggeration. In the context of the universe, 2.5 million light years is genuinely close. The observable universe is about 93 billion light years across. The nearest large galaxy cluster, the Virgo cluster, is about 54 million light years away. That's more than 20 times the distance to Andromeda. The Coma cluster is about 320 million light years away. The most distant galaxies we've observed are more than 13 billion light years away, so far that the light we see from them left when the universe was less than 1 billion years old. In this context, Andromeda at 2.5 million light years is practically next door. It's like the difference between your neighbor's house and a city on the other side of the planet. Yes, your neighbor's house is still across the street, still separated from yours by a real physical gap. But compared to a city 10,000 miles away, it's right there. This is why Andromeda matters so much to astronomy. It's close enough that we can study it in extraordinary detail. We can resolve individual stars. We can identify star clusters, nebulae, and dust lanes within it. We can measure the motions of its stars and the rotation of its disk. We can map its satellite galaxies and trace the streams of debris from galaxies it has consumed. We can study its supermassive black hole and the activity around it. We can do real, detailed, granular science on Andromeda in a way that we simply cannot do with more distant galaxies. For a galaxy 2.5 million light years away, that's astonishing. It speaks to both how relatively close Andromeda is and how powerful our telescopes have become. But how do we actually know it's 2.5 million light years away? How do you measure a distance that vast? You can't stretch a tape measure across intergalactic space. You can't bounce a radar signal off another galaxy and time the echo. The distances are simply too large for any direct physical measurement. Instead, astronomers use a series of ingenious techniques, each one building on the last, like rungs on a ladder. This approach is called the cosmic distance ladder, and the distance to Andromeda has been measured using several of its rungs. The most historically important method, and the one that settled the question of Andromeda's nature in the 1920s, is the Cepheid variable method. Cepheid variables are pulsating stars. They expand and contract rhythmically, brightening and dimming in regular cycles. The key discovery made by Henrietta Leavitt in 1912 was that a Cepheid's pulsation period is directly related to its intrinsic luminosity. A Cepheid that pulsates slowly is genuinely brighter than one that pulsates quickly. This relationship is consistent and predictable, which means that if you can measure how long a Cepheid takes to complete one pulsation cycle, you can calculate how bright it truly is. Once you know how bright a Cepheid truly is, and you can measure how bright it appears from Earth, you can calculate how far away it must be. A star that's genuinely very bright but appears very faint must be very far away. The math is straightforward, the technique is elegant, and when Edwin Hubble identified Cepheid variables in Andromeda in 1923 and applied Leavitt's relationship, he calculated a distance that placed Andromeda far beyond the Milky Way. His initial estimate of about 900,000 light-years was too low because the Cepheid calibration available at the time was imperfect. Over the following decades, as astronomers refined their understanding of Cepheid luminosities and accounted for different populations of these stars, the distance to Andromeda was revised upward to its current value of about 2.5 million light-years. The Cepheid method remains one of the most important distance indicators in all of astronomy. The Hubble Space Telescope has been used to identify and measure Cepheids in dozens of galaxies, extending the technique to distances of tens of millions of light-years. For Andromeda specifically, the Cepheid distance is well established. Based on hundreds of these pulsating stars that have been identified and measured within the galaxy. But Cepheids aren't the only tool. Another method used to measure Andromeda's distance is called the tip of the red giant branch method. This technique relies on a physical property of old, low-mass stars. As these stars age and exhaust the hydrogen in their cores, they swell into red giants. They climb what astronomers call the red giant branch, growing brighter and redder over time. But there's a maximum brightness that these stars reach before they undergo a sudden internal change, a helium flash in their cores that causes them to shift to a different evolutionary state. This maximum brightness is remarkably consistent across different environments and different galaxies. It acts as a standard candle, an object of known intrinsic brightness that can be used to measure distances. By identifying the brightest red giant branch stars in Andromeda and comparing their apparent brightness to their known intrinsic brightness, astronomers can independently calculate the distance. The result is consistent with the Cepheid measurement, about 2.5 million light-years. There are other methods as well. Eclipsing binary stars, pairs of stars that orbit each other and periodically block each other's light, can be used to determine distances. Planetary nebulae, The glowing shells of gas expelled by dying stars have a characteristic brightness distribution that can serve as a distance indicator. Red clump stars, a specific population of evolved stars with known luminosities, provide yet another independent check. All of these methods converge on the same answer. Andromeda is about 2.5 million light-years from the Milky Way. The consistency across multiple independent techniques gives astronomers high confidence in this number. It's not a guess. It's not an approximation. It's one of the most well-determined extragalactic distances we have. And because that distance is so well determined, and because it's cosmically short, astronomers have been able to do something remarkable with Andromeda that they cannot do with almost any other galaxy. They've resolved it into individual stars, not as a blur, not as a smudge of average light. Individual stars, one by one, millions of them. Between 2010 and 2013, the Hubble Space Telescope conducted a program called the Panchromatic Hubble Andromeda Treasury Survey. The telescope imaged roughly a third of Andromeda's disk in extraordinary detail, cataloguing over 117 million individual stars. Not galaxies, not clusters, individual stars. Each one is a separate sun, resolved as a distinct point of light from 2.5 million light-years away. The mosaic of images produced by this survey is one of the most detailed astronomical images ever assembled, containing thousands of individual Hubble exposures stitched together into a single panoramic view of Andromeda's stellar population. Think about what that means. From a distance of 2.5 million light-years, we can pick out individual suns in another galaxy, measure their brightness, determine their color, estimate their age, and classify their type. We can distinguish young blue stars from old red giants. We can identify star-forming regions and map where new stars are being born. We can trace the spiral arms not as vague structures, but as concentrations of specific types of stars. This level of detail is only possible because Andromeda is close. For galaxies hundreds of millions or billions of light-years away, individual stars blur together into smooth, unresolved light. Andromeda is near enough that we can study it star by star. Now, here's something that should stop you in your tracks. You can see this galaxy, this object 2.5 million light-years away, with your naked eye. No telescope, no binoculars, no special equipment of any kind, just your eyes, the same biological instruments that your ancestors used to scan the African savanna for predators. Those eyes evolved to detect the movement of a lion in tall grass or the ripening of fruit on a tree, are sensitive enough to detect the combined light of 1 trillion stars in a galaxy 2.5 million light-years away. That's extraordinary. It's one of the most remarkable things about the human visual system, and it's one of the most remarkable things about Andromeda. Think about what's actually happening when you look at Andromeda on a clear night. Photons, individual particles of light, left Andromeda about 2.5 million years ago. They left stars in a distant galaxy and began traveling through the void of intergalactic space at 300,000 kilometers per second. For 2.5 million years, these photons traveled in a straight line through empty space, crossing the enormous gulf between galaxies. They pass through the diffuse gas of the circumgalactic medium. They entered the outskirts of the Milky Way's own halo. They pass through the outer regions of our galaxy, past countless stars and gas clouds, until finally they reached Earth. They entered the atmosphere, passed through layers of air, and landed on the retina of your eye, Your optic nerve converted them into electrical signals. Your brain processed those signals and assembled them into an image. And you saw a faint smudge of light in the night sky. That faint smudge is not what Andromeda looks like right now. It's what Andromeda looked like 2.5 million years ago. The light you see tonight is ancient light. It left Andromeda during a period of Earth's history when the genus Homo was just beginning to emerge. Homo habilis, one of the earliest members of our genus, was making simple stone tools in East Africa around that time. The Great Rift Valley was populated by early hominids who were just beginning to develop the manual dexterity and cognitive abilities that would eventually lead to modern humanity. The African landscape was dominated by expanding grasslands and shifting climate zones. The ice ages of the Pleistocene were underway, glaciers advancing and retreating across the northern continents. When the light you see from Andromeda tonight began its journey, none of the things we associate with human civilization existed. No language, no fire, no agriculture, no cities, no writing, no technology of any kind, not even fully modern Homo sapiens, who wouldn't appear for another roughly 2 million years. The light from Andromeda has been traveling through space for the entire duration of human evolution. Every step from Homo habilis to you, from crude stone choppers at Olduvai Gorge to the smartphone in your pocket, happened while these photons were crossing the intergalactic void. The entire story of humanity, everything we've ever done and ever been, fits within the travel time of a single beam of light from the nearest major galaxy. And that's just the light arriving tonight. Tomorrow night, new photons will arrive, photons that left Andromeda one day later, roughly 2.5 million years ago, plus 1 day. The galaxy you see is a continuously arriving message from the past. A slow-motion movie of a distant galaxy playing out one night at a time, each frame separated from the last by 1 day of light travel, but representing the galaxy at nearly the same moment in its ancient past. If something dramatic happened in Andromeda right now, at this very instant, if a massive burst of star formation erupted across its disk, or a supernova chain lit up its spiral arms, we would have no way of knowing. The light from that event would begin traveling toward us at 300,000 kilometers per second, but it would take 2.5 million years to arrive. Whatever is happening in Andromeda at this moment, we won't see it for 2.5 million years. By then, humanity as we know it will almost certainly have transformed beyond recognition, if we still exist at all. The Andromeda we observe is always the Andromeda of the deep past, never the Andromeda of the present. We are permanently separated from its current reality by a gulf of time as vast as the gulf of space between us. This time lag applies in both directions, of course. If there were observers in Andromeda looking back at the Milky Way tonight, they would see our galaxy as it was 2.5 million years ago. They wouldn't see human civilization. They wouldn't see Earth as it is today. They would see the Milky Way during a time when the most advanced beings on our planet were early hominids, barely beginning to experiment with stone tools. They would have no reason to suspect that one unremarkable star in one of the Milky Way's spiral arms would, 2.5 million years later, host a species capable of building telescopes and studying their galaxy in return. This is the paradox of proximity across cosmic distances. Andromeda is close enough to see with the naked eye, close enough to study in extraordinary detail, close enough to resolve into individual stars with powerful telescopes. And yet, It's so far away that the light we see from it tonight is older than our species. It's close and distant at the same time, near enough to feel like a neighbor, but far enough that the neighbor you're seeing is a version that existed before you were even a possibility. There's another aspect of Andromeda's distance that's worth understanding. Andromeda is one of very few galaxies in the universe that is moving toward us rather than away from us. Almost every galaxy beyond our local group is receding, carried away by the expansion of space. The universe is expanding, and that expansion carries distant galaxies farther from us over time. But Andromeda is close enough that the gravitational attraction between it and the Milky Way overwhelms the expansion of space between them. The two galaxies are falling toward each other. This was first discovered in 1912 by Vesto Slipher, who measured the spectral shift of Andromeda's light and found that it was blue shifted. Blue shift means the light waves are compressed, which happens when an object is moving toward you. This was one of the earliest measurements of a galaxy's motion along the line of sight. Slipher found that Andromeda is approaching the Milky Way at roughly 110 kilometers per second. That's about 396,000 kilometers per hour. It sounds fast, and by human standards it is, but compared to the distance between the two galaxies, it's a crawl. At 110 kilometers per second, closing a gap of 2.5 million light years takes billions of years. The closure speed has been refined by modern measurements and is now estimated at roughly 110 to 120 kilometers per second when considering only the radial component, the speed directly along the line between the two galaxies. There's also a smaller sideways component to the motion, but the dominant movement is toward each other. The two galaxies are drawing closer, year by year, century by century, millennium by millennium. The gap narrows, slowly but relentlessly. In about 4 to 5 billion years, they'll meet. But for now, the point is this. Andromeda's approach toward us is only possible because it's close enough for gravity to overcome cosmic expansion. If Andromeda were 10 times farther away, the expansion of space would dominate, and it would be receding from us like almost every other galaxy beyond the local group. The fact that it's approaching is itself evidence of how close it is in cosmic terms. Let me try one final way of capturing this distance, because I think it helps crystallize the paradox. If you compress the entire history of the universe, all 13.8 billion years of it, into a single calendar year, with the Big Bang on January 1st and today on December 31st at midnight, then the light you see from Andromeda tonight left that galaxy on roughly December 31st at about 10:25 in the evening, roughly an hour and a half ago on the cosmic calendar. That's how recent Andromeda's light is in cosmic terms. The universe has been around for the entire year, and Andromeda's light only needed the last 95 minutes to make the journey. In a universe that's almost 14 billion years old, 2.5 million years is barely an eye blink. The light is young, the distance is small, the galaxy is right there. And yet that 6 hours on the cosmic calendar corresponds to 2.5 million actual years. 2.5 million years of photons streaming through black, empty space at the fastest speed the universe allows. 2.5 million years during which an entire species evolved from primitive hominids into beings capable of understanding what they're seeing when they look at that faint smudge of light in the night sky. That is what 2.5 million light years means. It means close enough to see, far enough to humble, close enough to study, far enough to never visit, close enough to feel like a neighbor, far enough that the neighbor you're seeing existed before you did. It's a distance that lives in the strange middle ground between the reachable and the unreachable, between the familiar and the incomprehensible. Andromeda sits in that middle ground, the nearest major galaxy, close enough to touch with your eyes, but separated from you by a gulf that no human technology could ever cross. A gulf measured not just in space, but in time, in evolution, in the entire unfolding story of what it means to be human. And yet, despite all of that, these two galaxies are connected. Not just by the light that travels between them, not just by the gravity that draws them together, but by the fact that they are both part of the same cosmic structure. The local group, bound together in a gravitational embrace that has lasted for billions of years, and will culminate billions of years from now in one of the most spectacular events the universe has to offer. These two galaxies, separated by an ocean of empty space so vast it defies the human mind, are falling toward each other, slowly, steadily, inevitably. And when they finally meet, when 2.5 million light years of empty space finally closes to zero, the result will reshape both galaxies forever. The Milky Way and Andromeda are falling toward each other at roughly 110 to 120 kilometers per second. That's a speed that sounds dramatic, and by human standards it is. A bullet from a high-powered rifle travels at about 1 kilometer per second. These two galaxies are approaching each other at more than 100 times that speed. But against the scale of 2.5 million light years, it's agonizingly slow. The gap shrinks by about 1 light year every 2,700 years. At that rate, it will take roughly 4 to 5 billion years before the two galaxies meet. That's a timescale comparable to the remaining lifespan of our Sun. The Sun has about 5 billion years of hydrogen fuel left before it begins to swell into a red giant. The Andromeda collision will happen around the same time, give or take a few 100 million years. These are the kinds of coincidences the universe produces when you're dealing with timescales this long. Two of the most significant events in Earth's cosmic future, the death of the Sun and the merger of the galaxies, will unfold in roughly the same epoch. But what will actually happen when these two galaxies meet? Most people, when they hear the word collision, picture a catastrophic impact. Two enormous objects smashing into each other, debris flying everywhere, destruction on an unimaginable scale. And in some ways, that intuition isn't entirely wrong. The gravitational forces involved will be immense. Both galaxies will be profoundly and permanently altered. But the reality of a galaxy merger is far stranger and far more subtle than a simple crash. Here's the key fact that changes everything. Galaxies are mostly empty space. The distances between stars within a galaxy are enormous compared to the sizes of the stars themselves. In the Milky Way's neighborhood, stars are separated by an average of about 4 to 5 light years. Each star might be 1 million kilometers across, but the gap to the next star is roughly 40 trillion kilometers. That's a ratio of about 30 million to 1. Stars are specks, separated by vast oceans of nothing. Even in the denser central regions of galaxies, where stars are packed more tightly, the distances between them are still enormous compared to their sizes. This means that when Andromeda and the Milky Way pass through each other, individual stars will almost never collide. The odds of any two stars hitting each other during the merger are vanishingly small. It's like throwing 2 swarms of bees at each other. The individual bees will pass through the gaps between other bees without touching. There are simply too few solid objects and too much empty space for direct collisions to be common. The stars will sail past each other, barely noticing each other's presence on an individual level. But on a larger scale, everything changes. Because while individual stars won't collide, the gravitational fields of the two galaxies will interact in dramatic ways. Gravity doesn't require contact. It operates across distance. And when two massive systems containing hundreds of billions of stars each pass through the same volume of space, the combined gravitational effects are transformative. Computer simulations of the merger, run on some of the most powerful supercomputers in the world, show what will happen in remarkable detail. The two galaxies will approach each other over billions of years. As they draw closer, their mutual gravity will begin to distort their shapes. Tidal forces, the same kind of forces that cause ocean tides on Earth, will stretch and warp both galaxies. Long streams of stars will be pulled out of each galaxy, flung into intergalactic space like cosmic streamers. The beautiful spiral arms of both galaxies will be disrupted, twisted, and eventually destroyed as gravitational forces overwhelm the ordered rotation that maintained spiral structure. The first close pass will be the most dramatic. The two galaxies will plunge through each other, their central regions passing within a few tens of thousands of light years of each other. During this passage, enormous quantities of gas will be compressed. When gas is compressed, it heats up and collapses into new stars. The first close pass will trigger a massive burst of star formation, lighting up both galaxies with billions of new stars. Entire regions that were quiet and dormant will suddenly blaze with the light of young, hot, blue stars. The combined system will briefly become one of the brightest objects in the local group. A starburst galaxy visible across millions of light years. But the first pass won't be the end. The two galaxies will pass through each other and continue outward, their momentum carrying them apart. But gravity will slow them down, stop them, and pull them back together. They'll fall toward each other again, pass through each other a second time, triggering another burst of star formation. Another round of tidal disruption, more stars flung into intergalactic space. This process will repeat several times over the course of 1 to 2 billion years. Each pass brings the two galaxies closer to their final state. Each pass strips away more of their original structure. Each pass mixes their stellar populations more thoroughly. Eventually, after several passes and billions of years of gravitational interaction, the two galaxies will settle into a single merged structure. The spiral arms will be gone. The flat rotating disks will be gone. What remains will be a large elliptical galaxy, a massive, roughly spherical collection of stars with no organized spiral structure. The ordered rotation that characterizes spiral galaxies will be replaced by the random, chaotic stellar orbits that characterize ellipticals. Stars will orbit the center of the merged galaxy in all directions and at all angles, like bees swarming around a hive rather than horses running around a track. Some astronomers have nicknamed this future galaxy Milkomeda. Others call it Milkdromeda. Neither name is official and neither is particularly elegant, but the galaxy itself will be impressive. It will contain roughly 1.5 trillion stars. The combined stellar populations of both the Milky Way and Andromeda, minus whatever stars were flung into intergalactic space during the merger. It will be one of the larger galaxies in the local group, though even Milkomeda won't be remarkable by the standards of the wider universe. Giant elliptical galaxies like IC 1101, which contains about 100 trillion stars, would still dwarf it. The two supermassive black holes at the centers of each galaxy will also eventually merge. Sagittarius AY star, the Milky Way's central black hole at about 4 million solar masses, and Andromeda's central black hole at roughly 100 million solar masses, will spiral toward each other over hundreds of millions of years after the galaxies merge. As they orbit each other, drawing closer and closer, they'll emit gravitational waves, ripples in the fabric of space-time itself. These gravitational waves will carry energy away from the system, causing the black holes to spiral inward faster and faster until they finally collide and merge into a single, larger black hole with a combined mass of over 100 million suns. That final merger will produce a burst of gravitational waves so powerful that it will be detectable across the observable universe by the right instruments. Now, should anyone on Earth worry about this? No, for several reasons. First, as I mentioned, actual stellar collisions will be incredibly rare. The stars in the Milky Way will pass through the approaching galaxy like ghosts walking through walls. Our sun, if it still exists at that point, will almost certainly survive the merger without any direct physical impact from another star. Second, the sun will be in its final stages of life by the time the merger happens. In 5 billion years, the sun will have exhausted its hydrogen fuel and begun swelling into a red giant, eventually expanding to engulf the inner planets. Earth's oceans will have boiled away long before the merger begins. Life on Earth, at least as we know it, will have ended not because of Andromeda, but because of the natural aging of our own star. Third, even if humanity somehow survives that long, perhaps by migrating to other star systems or developing technologies we can't currently imagine, the merger itself would unfold over billions of years. It wouldn't be a sudden event. It would be an unimaginably slow transformation, playing out over timescales far longer than the entire current history of life on Earth. No generation would experience it as a catastrophe. Each generation would see the sky looking slightly different from the previous one. Stars in slightly different positions, the shape of the galaxy subtly altered. But the changes would be so gradual that they'd be imperceptible on any human timescale. What those future observers would see, however, would be breathtaking. As Andromeda draws closer over the next few billion years, it will grow larger and larger in the night sky. Right now, Andromeda's visible extent covers about 3 degrees of sky, roughly 6 times the apparent width of the full moon, though most of that is too faint for the naked eye. As the galaxy approaches, it will appear to swell. In 2 billion years, it will be noticeably larger. In 3 billion years, it will dominate the night sky, a vast spiral stretching across a huge patch of the heavens. In 4 billion years, just before the first close pass, Andromeda will fill a significant fraction of the visible sky, its spiral arms stretching from horizon to horizon, its billions of stars visible as a breathtaking river of light, far more dramatic than the Milky Way's band across our current sky. The night sky of that distant future will be one of the most spectacular views in the history of this planet. A front row seat to a galactic encounter unfolding in real time across the heavens. Let me walk you through that transformation more slowly, because it deserves more than a passing mention. It will be one of the most visually stunning sequences in the history of this planet, playing out over billions of years, and each era will have its own character. In about 1 billion years from now, the change will be subtle. Andromeda will be somewhat closer, having closed roughly a sixth of the remaining distance. An observer looking up at the night sky would see Andromeda appearing slightly larger, slightly brighter than it does today. With the naked eye, the change would be almost imperceptible from one century to the next. You'd need to compare careful astronomical measurements taken centuries apart to confirm that the galaxy was growing in apparent size. But it would be growing, slowly and steadily, a few fractions of a degree wider with each passing millennium. In about 2 billion years, the change becomes more noticeable. Andromeda will have closed roughly a third of the remaining distance. Its apparent size in the sky will have grown noticeably. Where today it appears as a faint smudge covering about 3 degrees of sky, in 2 billion years, it will span perhaps 4 to 5 degrees, a larger, brighter presence becoming visible even from modestly light-polluted areas. Its spiral structure will be clearly visible to the naked eye on dark nights, the arms tracing elegant curves across the sky. For the first time in history, the inhabitants of this planet, whatever they might be, will be able to see the detailed structure of another galaxy without any optical aid. Andromeda will no longer be an astronomical curiosity. It will be a dominant feature of the night sky, impossible to ignore. In about 3.5 billion years, the approach enters its most visually dramatic phase. Andromeda will be close enough that its apparent size in the sky begins to rival the Milky Way's own band of light. Imagine looking up and seeing 2 galaxies stretching across your sky. Your own seen from the inside as a band of light, and another seen from the outside as a vast tilted spiral. The 2 structures will appear to be reaching toward each other across the darkness, separated by a shrinking gap of empty sky. Tidal effects will already be beginning to distort both galaxies. Faint tidal streams may be visible, wisps of stars being pulled from the outskirts of each galaxy by the other's gravity. The sky will look unlike anything any human has ever seen. In about 4 billion years, just before the first close pass, Andromeda will essentially fill the sky. Its disk will stretch from horizon to horizon on dark nights, a colossal spiral of light dominating the heavens. Individual bright stars and star-forming regions within Andromeda will be visible as distinct points and patches of light, embedded within the larger galactic structure like jewels set in an enormous glowing band. The sight will be simultaneously beautiful and overwhelming. 2 galaxies, each containing hundreds of billions of stars, occupying the same sky, about to pass through each other for the first time. During and after the merger itself, the experience becomes stranger still. As the 2 galaxies interact, some star systems will be flung out of both galaxies entirely. Gravitational interactions during close passes can accelerate individual stars, or even entire star systems, to speeds high enough to escape the combined gravitational pull of both galaxies. These ejected stars will drift into intergalactic space, orphaned suns wandering the void between galaxies, no longer part of any larger structure. Some models suggest that as much as 10 to 20% of both galaxies' stars could be scattered into intergalactic space during the merger. These would become rogue stars, still shining, possibly still hosting planets, but drifting through the vast emptiness between galaxies with no galactic home. If a planet orbited one of these ejected stars, its inhabitants would see something haunting. No band of light across the sky, no dense fields of stars, just their own sun and perhaps a few companion planets. surrounded by an almost starless void, with the merged galaxy visible as a distant glowing cloud, the home they were thrown from, receding slowly into the darkness. They would be the loneliest worlds in the universe, islands of light in an ocean of nothing. And then, during and after the merger, the sky will transform further. New stars will blaze to life in the starburst regions. Tidal streams of stars will arc across the sky like luminous bridges. The familiar constellations will be gone, replaced by an entirely new arrangement of stars as the merged galaxy settles into its final form. The descendants of everything alive today, if any still exist, will live under a completely different sky, in a completely different galaxy, with no trace of the spiral structure that once defined both the Milky Way and Andromeda. We actually have examples of this process happening right now, elsewhere in the universe. The Andromeda Galaxies NGC 4038 and NGC 4039 are two spiral galaxies currently in the process of merging. They're about 45 million light years from Earth, and they show exactly what happens during a galactic collision. Long tidal tails of stars stretch outward from both galaxies, giving the system its antenna-like appearance. The overlapping region between the two galaxies is ablaze with star formation, thousands of new star clusters forming in the compressed gas. The spiral arms of both galaxies are already disrupted, twisted beyond recognition by gravitational forces. In a few 100 million years, the antennae will settle into a single elliptical galaxy, just as the Milky Way and Andromeda will do billions of years from now. Looking at the antennae today is like looking at a preview of our own galaxy's future. But I want to pull back from the merger now and ask a bigger question. Because the collision between the Milky Way and Andromeda, while dramatic, is just one episode in a much larger story. The deeper question is this: what does the true scale of Andromeda teach us about galaxies in general? What does it reveal about the universe that we didn't appreciate before we understood how large this nearest major galaxy really is? The first thing Andromeda teaches us is that galaxies are far larger than they appear. This matters because it's so fundamentally important. When you see a photograph of a galaxy, you're seeing the bright, dense inner regions where stars are concentrated enough to produce detectable light. But the galaxy extends far beyond that. The stellar halo, the gaseous envelope, the dark matter scaffold, the satellite system, all of these components extend the galaxy's true physical extent, far beyond what any image shows. Andromeda's visible disk is about 220,000 light-years across. Its stellar halo extends to at least 500,000 light-years. Its gaseous halo reaches over 1 million light-years. Its dark matter halo may span nearly 4 million light-years in diameter. The bright part you see in photographs represents less than a quarter of the galaxy's full stellar extent, and a tiny fraction of its total gravitational domain. This is true of all galaxies, not just Andromeda. Every galaxy is far larger than it appears. Every galaxy is an iceberg, with most of its structure hidden below the surface of visibility. The second thing Andromeda teaches us is about perspective. We live inside the Milky Way. We can't see it from the outside. We can't step back and view our own galaxy the way we view Andromeda. This means that our intuitive sense of the Milky Way's size, shape, and structure is necessarily limited. We've learned an enormous amount about the Milky Way using radio, infrared, and microwave observations that can penetrate dust. The Gaia spacecraft has mapped nearly 2 billion stars with unprecedented precision. But we're still mapping from the inside, still trying to see the forest from among the trees. Andromeda gives us the external view that we can never have of our own galaxy. When astronomers study Andromeda's disk structure, its spiral arms, its dust lanes, its halo, its satellite system, they're learning about what a major spiral galaxy looks like from the outside. And what they have learned is that the Milky Way, while impressive, is the smaller of the two. Andromeda's disk is wider, its star count is higher, its halo extends farther, its central black hole is more massive. In almost every measurable dimension, Andromeda exceeds the Milky Way. This doesn't make the Milky Way unimportant. The Milky Way is still among the largest 5% of all galaxies in the observable universe. It's still a cosmic giant by any reasonable standard. But Andromeda's larger size forces us to recalibrate our sense of what normal looks like for a major galaxy. We might assume, living inside the Milky Way, that our galaxy represents the typical upper end of galaxy size. Andromeda shows us that it doesn't. There are larger galaxies right next door. The third lesson is about the nature of cosmic neighborhoods. The local group, our collection of roughly 50 galaxies, is dominated by 2 large spirals and surrounded by dozens of dwarfs. This pattern repeats throughout the universe. Wherever you find a large galaxy, you find smaller ones orbiting it, gravitationally bound to it, slowly being shaped and consumed by it. The relationship between a large galaxy and its satellites is one of the fundamental dynamics of cosmic structure. Andromeda, being both large and nearby, gives us the best laboratory for studying this dynamic in detail. We can watch galactic cannibalism in action as M32 and other satellites are slowly consumed. We can trace the debris streams left behind by already consumed galaxies. We can study how a dominant galaxy shapes its environment over billions of years. The fourth and perhaps most profound lesson is about our place in the cosmos. For most of human history, we thought Earth was the center of everything. Then we learned it orbits the sun. Then we learned the sun is just one star among billions in the Milky Way. Then we learned the Milky Way is just one galaxy among trillions. Each discovery pushed us further from the center, further from any claim to cosmic importance based on location or size. Andromeda adds another layer to this humbling progression. Not only is the Milky Way just one galaxy among trillions, it's not even the largest galaxy in its own neighborhood. The nearest major galaxy is bigger. When you look up at the night sky and see that faint smudge in the constellation Andromeda, you're looking at something that outscales your entire galaxy. Your sun, your solar system, your planet, and every star you can see with your naked eye are all contained within a structure that is smaller than the one you're looking at. The Milky Way, with all its hundreds of billions of stars, with all the complexity and beauty and life it contains, is the smaller sibling in this particular cosmic family. And yet, there's something about that fact that should give you not despair, but perspective. Because the Milky Way, smaller though it may be, is the galaxy that produced you. It's the galaxy where at least one planet developed liquid water, an atmosphere, and a biosphere complex enough to produce conscious beings capable of studying the galaxy next door. It's the galaxy where atoms assembled themselves into creatures that can look up at Andromeda and understand what they're seeing. Creatures that can measure its distance, count its stars, map its structure, and predict its future collision with their own home. Size isn't everything. A galaxy's importance isn't measured in light years or stellar populations. It's measured in what happens within it. And within the Milky Way, something extraordinary happened. Life arose, consciousness emerged, and for the first time in the history of the local group, one galaxy produced beings capable of studying the other. When you look at Andromeda tonight, you're participating in something ancient and remarkable. You're seeing light that has traveled for 2.5 million years across the void between galaxies. That light left Andromeda when your ancestors were barely beginning to experiment with stone tools, and it arrives at your eye tonight, carrying information about a galaxy that is larger than your own. You're seeing the nearest major galaxy, the biggest structure in your cosmic neighborhood, the galaxy that will one day merge with yours to create something entirely new. You're seeing it with the same eyes that your ancestors used to watch for predators on the savannah. Eyes that were never designed for this purpose, but that turn out to be just barely sensitive enough to detect the combined glow of 1 trillion distant suns. There's a strange intimacy in that. Andromeda is impossibly far away. No human will ever travel there. No signal we send will arrive in any reasonable time frame. The galaxy exists beyond our reach in every practical sense, and yet we can see it. We can study it. We can understand it. We can even predict its future with reasonable confidence. The distance between us and Andromeda is vast, but the connection is real, forged by light and gravity across millions of light years of empty space. Galaxies are not permanent things. They grow, they merge, they evolve. The Milky Way we see today is not the Milky Way that existed 5 billion years ago. It has consumed smaller galaxies, accreted gas, formed new stars, and slowly evolved into its current form. And 5 billion years from now, it won't exist at all, at least not in its current form. It will have merged with Andromeda, becoming part of something larger, something different, something new. The spiral arms will be gone. The flat disk will be gone. The constellations will be gone. What remains will be a single massive elliptical galaxy containing the combined stars of both parent galaxies, orbiting a merged supermassive black hole surrounded by the remnants of consumed satellite galaxies. In a strange way, the fact that the Milky Way will one day merge with Andromeda is oddly comforting. It means our galaxy isn't static. It's part of a living, evolving cosmic story. The merger isn't an ending. It's a transformation. The stars of the Milky Way won't be destroyed. They'll continue to shine, orbiting within a new structure, part of a new galaxy with a new shape and a new history. The atoms that make up our sun, our planet, and our bodies will still exist in that merged galaxy billions of years from now. They'll be part of Milkomeda, scattered among 1.5 trillion other stars, orbiting a black hole of over 100 million solar masses. The story doesn't end. It changes. So what should you take away from all of this? What does the true scale of Andromeda mean for you? Standing on a small planet orbiting one ordinary star in a galaxy that's about to spend the next several billion years falling into its larger neighbor. It means that the universe is bigger than you think, even if you already think it's big. It means that galaxies are more complex, more layered, more extended, and more interconnected than any photograph can show. It means that the Milky Way, our home galaxy, is genuinely impressive, but not the biggest thing in its own neighborhood. It means that 2.5 million light years, a distance so vast that light itself needs 2.5 million years to cross it, counts as nearby in the vocabulary of the cosmos. And it means that right now, tonight, If the sky is clear and dark enough, you can look up and see all of this with your own eyes. A faint smudge of light that is actually 1 trillion stars in a galaxy larger than your own, connected to you across millions of light years by photons that have been traveling since before your species existed. Andromeda is not just a galaxy, it's a mirror. It shows us what a major spiral galaxy looks like from the outside, something we can never see for our own Milky Way. It shows us the scale of structures that we usually only experience from the inside, and it shows us our future, the merger that will one day transform our galaxy into something unrecognizable, something new, something that will contain the descendants of every star and planet in both galaxies. The next time you're outside on a clear dark night, find the constellation Andromeda and look for that faint smudge. It doesn't look like much. It never does. But now you know what it really is. You know it's an entire galaxy, larger than your own, containing 1 trillion stars, with a disk 220,000 light years across, a halo reaching 500,000 light years, a gaseous envelope extending over 1 million light years, and a dark matter scaffold stretching even farther. You know it's 2.5 million light years away, close enough to see with your naked eye, but far enough that the light arriving tonight is older than humanity. You know it's falling toward you, slowly, inevitably, and that in a few billion years, it will merge with your galaxy to create something entirely new. You know all of this because you're human, because your species, living on one small planet in one galaxy among trillions, developed the curiosity to look up, the intelligence to ask questions, and the ingenuity to find answers. You figured out the scale of Andromeda not by traveling there, which is impossible, but by catching its ancient light, analyzing it, and reasoning your way to the truth. That's remarkable. In a universe of silent galaxies and empty space, one species on one world managed to understand the galaxy next door. That says something about the universe. It says something about us. And it says something about what's possible when curiosity meets a clear dark sky. Sleep well tonight under the Milky Way. Our galaxy is vast and beautiful and home to everything we've ever known. But remember that just next door, visible to your own eyes if you know where to look, there's something even bigger. And it's heading this way.